So a lot of this should be familiar. I hope the rules are pretty similar to propositional logic. We're just adding a couple new things as far as the syntax and so on goes. So our system of inference for monadic predicate logic uses the rules for constructing derivations in predicate logic. Same thing applies here. We're going to have a couple new rules for removing and adding quantifiers, which will be important for being able to do proofs. A lot of the proofs that we're going to be doing involve just taking the quantifiers off, doing the work that we need with just the materials that the quantifiers that a quantified formula has within it, and then putting the quantifiers back on at the end of it. And we'll also have a rule for exchanging the universal and existential quantifiers, because as we'll see, it'll be possible to express universal statements in the form of an existential and vice versa. But there's some rules that we'll have to follow to do that. So most derivations require taking quantifiers off of well-formed formulas using the same rules that we had with predicate logic, then putting the quantifiers back on. So a lot of the proof work that we'll do should be in familiar territory. The only really new step here to learn at first is how do I take the material out of being existentially or universally quantified, and then how do I put it back on if I need to at the end. So instantiation rules allow us to take quantifiers off, and generalization rules allow us to put quantifiers on. And instantiation and generalization, either existential generalization or universal generalization, or universal instantiation or existential instantiation, are new rules that we'll use in proofs as justification for a new line. So universal instantiation is a rule of inference in predicate logic that follows for the removal, that allows for the removal of the universal quantifier when it is the main operator. This is very important. In order to use universal instantiation, the universal quantifier has to be the main operator of the formula that you're applying it to. So for any variable alpha and any formula f and any singular term beta, we get well, it looks like my slide's not showing up there, but we'll work through this example here. Well, actually, hold on. Annoying that it's not showing up. Well, we'll go ahead and use this slide as examples. So with a universal instantiation, there's a couple of things that we can do. Well, this is, first of all, basically the way it works is when we apply universal instantiation, we take off the universal quantifier, and then we just put whatever it applied to, whatever was in the scope of the universal quantifier, and we have to put the entire, whatever was in the entire scope of the universal quantifier on a line by itself. So here on our first line, our first premise, we have for all x's, if sx, then px. We'll use universal instantiation here with variables, with x's, to get rid of the quantifier and just say, well, if sx, then px. Now this by itself doesn't mean anything really, which is why if we want to, when we finish our proof, we're going to want to put a quantifier back on this so that it means something. However, with a universal instantiation, we can also instantiate using a constant instead of a variable. So because universal statements apply to everything, line 1 here says, for all things, if it has property S, then it has property P, then we can use a constant because since it applies for all things, any specific individual thing that we choose, it will also be the case that if that thing has property S, then that thing will have property P. So we can either instantiate using a variable, like in line 2, or we can instantiate using a constant in line 3. Now, which one of these we do is important because we can get back to a universal statement if we instantiated with a variable, we can use universal generalization to get back to for all x's if sx then px from line 2, but we could not do that from line 3. Well, of course we can get line 3 from line 1, because we know that if line 1 applies in all cases, then it will apply in the specific case of SB, if SB then PB. But because B is a constant and it refers to a specific thing, we can't go from what we know about that case and say it applies in all cases. So we can't get back to a universal from there. We'll talk about that more later on. It'll matter for when we do proofs. But the important point here is that though we can universally instantiate a universally quantified formula, either with constants or variables, we can't mix them up. So in line 4 here, we see that Sx, we have Sx as a variable, and PB, that the consequence of our conditional, is using a constant. That doesn't work. Whenever you instantiate, you have to, everything that is in the scope here that uses the same variable, for all x's, they have to be instantiated either as x's again, or as some constant that we choose that's the same. We can't mix them. Here, we have two constants, but they're different constants. So again, we can't do this. We can't say there is, for something A, if something A has property S, then something B has property P. That doesn't work. So with the universal statement, we can do two things. We can instantiate with variables, like in line 2, or we can instantiate with constants, like in line 3. But everything has to be instantiated using the same constant or the same variable. So universal generalization is a rule of inference in predicate logic that allows for the addition of a universal quantifier. So for any variable beta, any variable alpha, and any formula f not containing an a, we can get to we can move from a free variable that is using just a variable that isn't using a constant to saying that applies in all cases. So you must replace all occurrences of variables with a bound variable. Now, because we're sticking with just x's here, this shouldn't come up too much as a problem, but you can see that in line 1, we have if sy, then py, and y is a variable here. These are both open sentence that just means is p, if is p, then is, or if is s, then is p. By itself doesn't really mean anything. In order to get to it, back to it meaning something, we have to use a quantifier on it. And because we're using variables here, not constants, it's allowed for us to universally generalize. We can say for all x's, if x has property s, then x has property p. But again, we have to make sure that all of our variables, however we end up generalizing it, and the way that we're going to be doing things, we're going to pretty much, since we're sticking to using x's here, we should just it should just be x's across the board. This is going to matter more when we're working with constants, because constants are specific things, whereas variables are just kind of anything. But it's important that throughout the formula that you use, or when you universally generalize, that the variables that you use with the universally quantified formula are the same. So we can't go, well, this is wrong for a couple of reasons. We're missing the parentheses here as well, but also the x and y here are different variables. They should be the same, like in line 2. So you can go from line 1 to line 2, but not from line 1 to line 3. So one thing that we can't do then is that if we have something that is using a constant, we cannot universally generalize. So we can't go from fa to for all x's fx. So this is like moving from Antoine is French to everything is French. So we can only go from uh, an open sentence with three variables, where if I had fx here, which just is French, then I could move to everything is French. If we had is French for some reason um, in our proof, then we could universally generalize over that. But for anything that's talking about a specific concrete thing, and we'll know it's talking about a specific concrete thing because it'll be using a constant instead of a variable. In this case, a. You'll notice that it's not an alpha there that's being used, but just an a, which stands for something as concrete. Let's say in this case it stands for Antoine, but it'll stand for something concrete. Just because Antoine is French doesn't mean that everything is French. So you can't universally generalize over a constant. Now, existential generalization is a rule of inference in predicate logic that allows for the addition of an existential quantifier. So for any singular term beta, so again, singular term, so beta here is going to stand for just any constant, and any variable alpha and any formula f not containing alpha, we can go from some property applying to a constant to there is at least one thing that has this property. So we go from a specific thing here to a variable, and this works in this way. So existential generalization can be used on propositions whose singular term is a constant and on whose singular term is a variable. Both are permissible. Either way works. Because we know that from line 1, there is a thing A, whatever A is something concrete here. Because there is something A that has property B, then it's true that in line 2, there is at least one X that has property B. So when we existentially generalize, we change this constant from being a constant to being a variable. But we can do that because we're saying that all we're saying is that there is at least one thing that has property B. And we know that there is at least one thing property B because A has property B. The specific concrete thing A has property B. Now, we don't know what A is necessarily, but we know that it is a thing that has property B, so we're justified in saying there is at least one thing that has property B. Now, this is as opposed to saying for all x's bx, just because A has property B doesn't mean that for all things have property B. So we can't universally generalize from BA, but we can existentially generalize. We know that there is at least one thing that has property B. Now we can also existentially generalize from these unbound variables here. If our line was bx, we could also get to there is at least one thing, one x such that bx. We could do that with existential generalization. Now, in this case, we could also universally generalize. Now, because if it was true that for all x is bx, it would also be true that there is at least one x bx. That's a weaker claim than for all x is bx, but if it's true that for all x is bx, then it's also true that there is at least one thing bx. So we can use existential generalization in this case as well. So existential instantiation is going to be more limited than universal instantiation. So existential instantiation is a rule of inference in predicate logic that allows for the removal of the existential quantifier when it is the main operator. So just like with universal instantiation, when we have a universally quantified formula, we want to get the quantifier off of there so that we just get the parts into our proof and then we can manipulate and move them around. We can also do that with existentially quantified formulas, but it's more restricted. So for any variable alpha in any formula f and any new constant beta, we can existentially generalize in this way. So we'll have some existentially generalized formula. We can get rid of the existential quantifier, and we'll put in, instead of the variable alpha, we'll put a constant beta, which you can see here. But it's really important that whatever constant we put in is a new constant that has not appeared in any of the premises that we're looking for or the conclusion that we want to show. So we know that, so always have to use a new constant. If we know that there is something A that has property S, and on premise 2 we have there is at least one thing that has property Px and Tx, well, we can't, when we use existential instantiation, we have to change these variables out and make them constants. But when we change the variables out and make them into constants, it can't be the same constant that was used before. So just because we know that there is something A that has property S, we know that A has property S, and we know that there is at least one thing that has properties P and has properties T, we don't know that it's the same thing. So if we existentially generalize using A as our constant, this would mean that whatever A is, our singular concrete thing, has three properties, P, S, and T. And we don't know that that's the case from just premises 1 and 2. The thing that has properties P and T at the same time could be something else. So in order to be careful about that, whenever we use existential instantiation, we always have to use a new constant that hasn't been used before. So if we interpret SA as N is a scientist, PX as X is a person, and TX as X plays tennis, then we are inferring from N is a scientist and someone plays tennis to N plays tennis. So it doesn't, if we think about it in those terms, it doesn't follow. We don't know that just because there is a thing that has properties P and has properties T, that that thing is N. And we know that N, in this case, has property S. All right, so the generalization and instantiation rules are rules of inference, and as such can only be used on whole lines. So here, we would need some parentheses around the if Sx then Px in order to use universal instantiation. Right now, we have a formula that says if for all x is Sx, then it is the case that Px. But the universal quantifier is only applying to the Sx here. The major operator is the horseshoe, the conditional, not the universal quantifier. So we need the universal quantifier to be the main operator of the entire line in order to use universal instantiation. Very important. Also, when using universal instantiation, you should instantiate with a variable if you need to universally generalize later in the argument. Remember, because you can only universally generalize from a variable, but we can universally instantiate with either a constant or a variable. But if we need to get back to a universal statement, so we need to think ahead here a little bit when we're doing instantiation, what our end goal is. If our end goal is going to be a universal statement, then we need to keep it using variables rather than constants. So if we have the statement for all x's, if Sx then Px, and we instantiate with a constant in this case, we're using B. So if it's true that for all things, if that thing has property S, then it has property P, then it'll be true in any given concrete case. So we can instantiate using a constant if we want. So we use universal instantiation here to get if thing B has property S, then thing B has property P. Well, we can't universally generalize from there. If we needed to get back to a universally quantified formula, we couldn't do that from constants. So we would need to instantiate with a variable like x instead of p on line 2. So when you have an argument that requires both universal instantiation and existential instantiation, do existential instantiation first. This is because universal instantiation, when we instantiate with a constant, we can use a constant that has been used before. Because it applies universally to everything, then any constants that we're using, it should apply in those cases as well. But existentially quantified formulas only apply to specific things. So when we instantiate those, we have to use new constants that haven't been used before. Now, if we need both of these to work together and share the same constant, then we have to instantiate existentially first, and then we can universally instantiate using the same constant to make things compatible with each other. But the order here is very important. So if you first universally instantiate, then step 4 here isn't allowed. We have two formulas that we started with. First, there is at least one x such that x has property s and x has property d. And our second formula, our second premise is for all x's, if x has property s, then x has property p. If we universally instantiate first using a constant, we get, there is, if something b has property s, then b has property p. But we can't existentially instantiate with the same constant after that, because we have to use a new constant every time we existentially instantiate. However, that's not a restriction for universal instantiation. So if we existentially instantiate first, we get SB and DB. Then we can universally instantiate SB, if SB, then PB. That works perfectly fine. Now this is going to seem really pedantic, but it's important to be careful about the order that you universally instantiate and existentially instantiate. If you do these two things in the wrong order, even though it shouldn't affect the rest of your proof from here on out, we're getting the same result, but we need to do them in a certain order. You will lose points on an exam if you existentially instantiate in the wrong order like this, because this is just a misapplication of the rule. Existential instantiation using a constant that's already present in our proof is not allowed. So that would be, you would be applying a rule in the wrong way. So in general, existentially instantiate before you universally instantiate. Now, if we have multiple, so it is possible to instantiate a quantified proposition multiple times. However, when using existential instantiation, you must use a new constant each time. So for example, here we have two different existentially quantified formulas. So we're going to want to existentially instantiate them both. And so unlike universally quantified formulas that can use the same constants as happened before, if we want to instantiate each of these formulas, we're going to have to use new constants. So we can't get these to play nice with each other in the same way that we can get existentially quantified things to be compatible with universally quantified things. So for there is at least one x such that sx and dx, and line 2 says there is at least one x such that bx or ex, we can go ahead and existentially instantiate line 1 as SB and DB. We can do it again as SA and DA if we want. We can keep applying existential instantiation because we're just taking one of our premises and applying the rule existential instantiation as a justification to get this new premise. We can existentially instantiate our second premise here, but here we make a mistake. If we existentially instantiate premise 2 using B, well, B was already used here in line 3 as a constant. So every time we existentially instantiate, we have to use a new constant to make sure that we avoid making things compatible when they might not actually be compatible. Okay, next we'll talk about quantifier exchange, but that's enough for the first round of stuff as an introduction to predicate logic. Yeah, there'll be sort of more details about this as I work through the homework assignments. This was just sort of an introduction to what the rules are, and a lot of it can be kind of difficult to understand without more examples. So hopefully the homework solutions video should provide that for you if you got to the end of this still feeling a little bit lost. Predicate logic is usually where things get a little bit trickier for students. Um, Again, just take it slow. Make sure you understand one thing at a time. When you see a formula and you think, I don't know, just work through like one piece at a time what it means. Saying out loud to yourself what it stands for should help you process what's going on in it. Um, and yeah, so if you're confused at this point, of course, feel free to email me any questions that you might have, or come see me during my office hours. Um, but the watching the homework solutions might help because then we'll be working through concrete examples, and I'll be talking about why you should do a certain thing in this way or whatever. All right, that's all for this one.